Hello, the Astro 30 here, and today... What, sweet? Can you have another electronics video? Well, I guess, yeah. Yippee. Greetings, the Astro 30 here again with another exciting installment of AEL, Astro's Electronic Lab. Today I'm going to be building a very simple power supply, linear power supply. This kit is designed for what is known as the SC480. Now, that was a power amplifier that Silicon Chip around about February 2003 redesigned based on the old ETI 480, which was a 100 watt power amplifier module, which was, I think, designed in around about 1976. And thousands of those kits were built, and the actual output power was nowhere near what they said it was going to be. They came in two versions. You used two output transistors, 2N3055 and MJE2955 respectively for 50 watt, and you added an extra two transistors either side of opposite polarity, and you would end up with 100 watt. That was a bit of a wank factor because it wasn't true. I built about 4 of those power amplifiers. They were good rugged power amplifiers. They did the job. They had very high total harmonic distortion, however, and their output power before clipping was nowhere near what the measured performance was. I believe that when I actually built one back in 1996, I actually measured the output, and it only turns out to be around about 38 watt, so nowhere near 100 watt. Anyhow, that's detracting from what we're talking about today. This power supply is designed for the power amp module that they had redesigned. I'm not going to be using it for that. I'm going to be using it for that 115 watt power module I built a couple of weeks ago. And this just is basically a high side, low side current power supply. You've got your main, well, this is designed to run at plus minus 40 volt. That's with a 28028 transformer, and also provides a plus minus 15 volt rail to run preamplifiers. However, I'm going to be running it on plus minus 35, which should be alright. This intro is going on way too long, but basically all you get is the circuit board, the parts, and that's it. You have to provide your own transformer and whatever other connections you want to put onto it. They give you a recommended transformer, which is a MM1095 56 volt center tap transformer. You can't get that anymore from Jaycar. In fact, you can't get very many high powered transformers from Jaycar anymore. They seem to have totally discontinued them. No idea why, but you can still get high-powered toroidal transformers and E-course type transformers from Altronics. Anyway, before we have a look at the contents of this kit, let's have a look at the little block diagram I've drawn up over the week to show you what it is I'm doing and how everything interconnects. Okay, with any large-scale or even any medium-scale electronic assembly project such as what I'm doing, it's always a good idea to have a functional block diagram of what it is you're actually doing when you come to assemble the thing in the final process. So over here we've got our preamp, which is the K5340. That's the Altronics catalogue number. The unbalanced output of that is going into our 115 watt plastic power amplifier, which is the KC5347 Jaycar kit. Its output is then going to be fed into another kit, a speaker protector, which is Altronics K5167, which I don't have yet, and I may or may not use it because it's designed to run on a slightly higher power rail, because it was actually designed for a 135 watt ultra low distortion power amplifier, which is also another Silicon Chip project. So it may or may not work with the projected power that I'm going to be running into it, because it requires, I haven't shown it, but it also requires the AC input from one side of the transformer plus the DC rails for it to work. So that'll be explored in another video when I get this protector. That then goes out into our speaker driver, and notice here with the earth I've got a star. Over here with the earth I've got a star, and over here at the power supply, which is the SC480, which is what I'm building today, which is KC5347, Jaycar catalogue number. These earths with the star means it's going to be going to the star earth point somewhere in the middle of the chassis. So all the high power 0-volt rails return to one central point. And because this power amplifier is already designed with a star earth on the PCB, we're going to make use of it. And over here we've just got a toroidal transformer here, which is 240 volt primary, 25025 on the secondary, a 3 amp inline fuse, power switch, and that goes into the AC section of the power supply board. It's pretty much, well, simple. There's not really much there to discuss, but I just thought I would show this because it is also important to have a functional block diagram, as I said, so you can actually see where you're going with the project. And as I said, I've got a note down here, may or may not work with lower voltage. That remains to be tested. So that'll be explored in another video once I get that kit. That should be here in the next few days. So anyway, moving on with the next bit. Okay, that was gripping. Now to open this kit and have a look at the contents. I've already built one of these previously about 5 or 6 years ago. So I already have a set of instructions in my folder, but I'll hold on to them anyway. These are the bag of parts. They give you very limited solder. They even give you what looks like 3 10mm standoffs. Why 3? I don't know. There should be 4. Oh no, there's 4 in there. And the screws for it. That's nice. 2 50 volt 470 microfarad. Let's get my tongue untied. 2 50 volt 4700 microfarad capacitors. Yay, that took me about 10 times to say that correctly. Some high current diodes, which I believe are just 3 amp diodes. I'll look at the schematic in a minute. And some terminal connectors. Not very exciting, I know. So here's the PCB. Fairly standard 1.5mm thick fiberglass. Fairly hefty copper traces here. But again, nothing very exciting. But they do make this so you can actually cut this board off here down this dotted line and get rid of the low powered supply. But why you would do that, I don't know. So you've got 2 places here to put your high powered plus minus 40 volt rail connector. So you can choose either. I would probably put it as close to the capacitors as possible with the wires going in this way, because it gives you plenty of space to get the wires in there. If you put it up here against these capacitors, yeah, it's getting awfully difficult. So, okay, let's have a look at the schematic. So here's our schematic. We're looking at a 56 volt center tap transformer to provide plus minus 40 volt rails. And they're using a 3 amp inline fuse, which is actually after the switch, if you notice. Technically speaking, it doesn't really matter where you put the fuse, whether you put it before the switch or after the switch. However, putting it after the switch might be, from a safety standpoint, a good idea, because most of us humans, when we blow the line fuse on an amplifier, decide not to bother to unplug the bloody thing before unscrewing the fuse holder. And then grabbing hold of the fuse, and depending on how the fuse holder is wired, where the active wire from the mains comes in, you can get a shock off the fuse holder. So having the switch across before the fuse holder is probably a better idea. And And that goes into our 4-wave bridge rectifier, which is comprised of 4 times 1N5404s. So they're a 800 volt, I believe, 3 amp diode. So that allows us to draw 3 amps across that bridge rectifier, which should be more than enough for that 115 watt amplifier. No problems there. Goes into our 2 4700 microfarad 50 volt capacitors in the standard linear fashion, which gives us our 40, minus 40, 0 rail there. And you'll notice that they've put a little ground symbol here at this 0 volt connection. Now, as explained in the block diagram, that is where I'm going to take my 0 volt rail from the power supply and put it to the star earth of the case. And then the amplifier's 0 volt goes back to that star point as well. Moving on, we go through these 2.2k resistors, 1 watt devices, and that will give us roughly 1.1k 2 watts. So basically they're doubling up the resistors there to make it able to pass higher current. However, you're still using a 1 watt xenodiode here. Now this is basically the mirror image, so we ignore that section for now. This basically forms a shunt regulator using this xenodiode here. We take the output off between the resistor and the cathode of the xeno. That gives us a plus 15 volt rail, and the other end, the anode, forms the 0. They've also, looks like they put this ground point over here, which would connect to here rather than connecting it straight across. Okay. On the other side, we've got the same thing, basically 1.1k 2 watt resistor here, going into the anode of this xenodiode, which taken off the anode gives us our minus 15 volt, and the cathode is connected to 0. So that's our plus minus 15 volt rail shunt regulator. So it's not all that overly complicated. It's very easy to solder. I'm not going to do the assembly in time lapse. What's the point? It's a very, very simple circuit. It's not going to take me that long to assemble. And also it takes, believe it or not, even for only 15 seconds of video, it can take a couple of hours to render out a time lapse at 600% the speed. So I want to try and avoid doing that because I've actually got to make another video this afternoon, so I want to be able to edit and export this one and then start editing the second one. Yeah. So I'm going to get set up here. I'm going to put the board in my little jig. I'm going to start with all the low profile components like the xenodiodes, which are the smallest. Then moving up to the 1 watt devices like the 2K2s. And remember, with 1 watt resistors and including the 3 amp diodes, is to leave them slightly off the board just to give it a bit of an air gap. So if they overheat, it's not going to scorch the board, because if the board gets scorched anywhere where these high power devices are, that scar in the board can actually become conductive, and then you'll end up with all sorts of problems later on. So let's get started. Okay, so I'm going to get myself set up. The recommended construction time on this, according to the bit of yellow paper in here, is around 15 minutes. So I reckon that's all it's going to take. I'm going to reuse this tray to put my components in. I'm going to use up some solder I've had lying around from another kit. Might as well. So I'm going to start by opening the bag of components and just dropping them out into the tray. I've got some more solder, and yeah, we'll just basically go from there. They say 15 minutes, I reckon about 10. But I'm going to leave this running, and I'll choose what to edit in and out when I come to do post-production. Now there they are. I was just looking for where my xenodiodes were. There they are. That's what I'm going to start with first, is the xeno diodes. Would help if I had some tools. So I'm going to start by measuring where I need to bend the diodes. So I'm looking at about there, so about 6mm either side of the diode. So I'll just bend him with some pliers, like so, and pop him in the hole. Alright, that's nearly the completion of the construction, and it's been around about 12 minutes now. With the large filter caps, they've given us two types of hole plus a center location in case the capacitor has a center locating lead which isn't connected to anything. So they go in there. I think that's the right hole spacing for that. It's awfully tight, but nothing wrong with a tight fit. Please keep it clean, guys. Now, get this one to go in as well. These leads are all chewed. I don't know why that one won't go through. There we go. Right, so those are two large filters installed. Now all I have to do is just solder them in, and we can put the standoffs on, and the supply is complete. Should be no charge across that. No, it's not. For some reason I can smell burning plastic. Might be these burning. Might be touching it with a soldering iron or something, I don't know. Okay, that's that soldered in. And apart from a bit of mechanical of putting the standoffs in, that was roughly 15 minutes. So yeah, it can be built in 15 minutes time, and you'll have something that looks like that. So now I'm going to put my standoffs on, and then we'll get into some testing. And so we're nearly ready for testing. I've just used some component leads here, the cut-offs for my connections for my alligator clips. Another great use for scrap component leads. Now, for testing purposes, we need a suitable supply. This is where this comes in. This is a 25025 volt 160 VA toroidal transformer. So we'll just unbox the transformer. Now this is our mounting kit, so we don't want to lose that, so I'll put that to the side. And here, in some bubble wrap, is our donut, our transformer. There we go. Now, usually they mark on the transformers what fuse to use for the primary, but it doesn't. But I know from experience these 160 VA transformers require a 3 amp line fuse. So that'll be connected, those are the primaries. These will be connected the correct way around. So we're looking at the orange, yellow, black, red for each winding, but I can't remember which order it goes in because it's not marked, and I don't think I marked it down. So I'm going to have to look up this particular model transformer, which part of the winding is which, like where the actual 0 point is, etc. Hook it up to this, and then we'll hook it up to the mains lead that I've got lying around somewhere. Hook it up to some power and see if we can blow it up. Okay, and that was relatively easy to look up. Just looked at the data sheet. This is drawn basically in the reverse way you would actually wire it, with the neutral at the top, active at the bottom. But the little dots here just mean where the actual neutral points of the transformer are, so that they relate to this neutral. So that dot relates to the neutral, that dot relates to the neutral. So basically we've got orange, which is one neutral, black, which is the second neutral of the secondary. To keep them in phase, you join the black and the orange together. If you were putting these in parallel, the yellow and the reds are actually the secondary windings. But if we're going to be putting it in series, which is what I'm doing, the black would go to the yellow, orange would go to one side of the AC connection, and the red would go to the second side of the AC connection on the board. So that's how it's going to be wired. Okay, I've got the transformer hooked up to the board. Now trying to get both the 0 volt windings into the same hole on the terminal header can be a bit challenging, but it can be done. It doesn't really matter for all intents and purposes which direction you wire the AC wiring, like if you put the red over here and the orange over here or vice versa. It doesn't really matter as long as the secondary windings are in phase with each other. Put them out of phase and you'll either end up with half the voltage or no voltage at all. And if you wired them in parallel out of phase with each other, it would basically cancel itself out, so you'd have no voltage at all. So I've got it wired into a power plug on a terminal header. Now this is very, very, very safe. Not. If you're doing something like this to test something, you're doing it at your own risk, but just remember, do not come into contact with these live wires. Whenever you're mucking around with one of these terminal headers, unplug it from the wall first. I should say terminal block. You want to limit the risk of electric shock, but always give high voltage mains the respect it deserves. So don't mess with it if you don't know what you're doing. Anyhow, it's time to plug it in. I'm going to take a quick voltage measurement here on the high side and a voltage measurement here on the low side and see what voltages we get. I haven't checked first to see whether or not the transformer is any good, like it's doesn't have shorted windings. I should probably do that first. Yeah, I don't know how well you can see that. We've got 12.5 ohm across the primary, and across the secondaries we've got 0.4 there, but it's actually terminated into the board, so that could also have an effect. 0.5 of an ohm there. So what I'll do is I'll just lift one end of the secondary out of the board. Still at 0.5. Yep, it's not a short circuit. It's going to have a very low resistance anyway because of the number of turns. Anyhow, it should be safe to plug in. So we're about to find out. So I'm just going to stand up and stand well away from this when I plug the transformer in. Are we ready? Here we go. Well, I can hear the transformer buzzing, so I know it's working. Hopefully nothing's going to go bang at the moment. Let's have a measurement here. We've got 39 volt there on that side, 39 volt on that side, so that's fine. We have 0.8 of a volt on that side, but that's not loaded either. We've got 15 volt there, 0.8 of a volt there. That's not right. So our negative 15 volt rail is not working correctly. Just feeling these drop-in resistors here on that diode across the negative. They're getting quite hot and they're not actually going into any load. These ones on the other side are getting mildly warm, but not as hot as this one. So these must be drawing a lot of current somewhere. So for some reason we're drawing current, excessive amounts of current on this side. So that I'm not 100% sure of. It's not the transformer because I know we've got proper voltage across each of the high sides, so that's working fine. But for some reason the low side negative regulator or xenodiode is drawing excessive current, and well, I'm not sure why. It could be a short circuit, so I'll just check that the output's not shorted. Indeed it is. Well, it reckons it's not shorted. Hang on, just discharge my capacitors. Let's try that again. There should be no shorts on the output. No, there's no short circuits or anything that I can see, so that's fine. That's just excess residual voltage. Right, so our output is not shorted in any way. So for some reason the negative 15 volt Zeno is drawing current, and well, I'm not 100% sure why. We don't have any short circuits across these resistors. I mean, it's joined to where it should be, and yeah, there's something not quite right here. Alright, I lifted off one end of that diode, just because I can, and yeah, we've got 25 volts now there, so, excuse me, so I know with that diode out of circuit we're getting a drop of about 17 volts across these resistors. So I think there is something wrong with this Zeno diode. Be the most likely thing. There's something wrong with that diode. Although it does, on diode test, conduct correctly. We're getting a voltage drop of 0.7, so that is correct. So the diode is conducting. Reverse breakdown is also 0.7. So I don't know where to go from here really. It certainly looks like I am not going to be making a second video this afternoon until I can sort out what is going on with this negative 15 volt rail, because it shouldn't be at 0.8 of a volt. If this side's at plus 15, that should be at minus 15, but it's not. And the only thing in that circuit is the diode, and I have actually built this power supply module once before, a few years ago, and I know it does work. So what I might have to go out and do is go out and buy some new Zeno diodes. Okay, I've got the bench supply set up with plus minus 28 volts across the negative and positive sides of the bridge rectifier. The zero is just sitting here. So I'll turn the load on, and I'm getting a current draw of 20 mA, which is fine. Yep, and we're still at 0.8 of a volt on the 15 negative rail, and minus 14 thereabouts on the positive 14 on the other. So there is definitely something up with this shunt regulator, and it's beginning to do my head in. Okay, I'm back. I've got some diodes. I haven't changed it yet. I've taken off the 100 microfarad 16 volt capacitor here because I just realised I stuck 25 volt across it, so it wouldn't have made it very happy. So I've got the transformer disconnected for now. I've got the supply hooked up across the bridge rectifier again, and now I'm going to see if it's not just the capacitor causing the problem. So I'll turn it on. We've got 20 mA current draw on the supply. Let's see what our output voltage is. Still 0.8 volt, so I know there's still a problem there, so I'll just change that diode and see what happens. Okay, these are 1N SC480 xenodiodes for those playing at home along at home. Let's see, 0.6 volt that way, and there's no reverse breakdown voltage that way. So let me just get the old one. So we've got 0.7 that way, reverse the polarity, we have 0.7 volt that way. So that's the issue. This diode is practically shorted, so that's why it's not working. So if I now change this diode, we should have a minus 15 volt rail, and I'll replace the capacitor too. I've got some lower profile ones here, 16 volt 100 microfarads. Might as well change the other one whilst I'm at it so they look the same. Okay, capacitors are changed. I'm surprised that little 16 volt didn't blow up. And the Zener is now changed. So I'll now turn it on and do another check. Well, lo and behold, we now have a minus 15 volt rail and a positive 15 volt rail. Isn't that special? So all of that for about an 80-cent component that just happens to be short-circuited. Now, that's why it always pays to do a reverse breakdown check of diodes before installing them. There shouldn't be any voltage there, so that's a good indication that this one is stuffed. So now that that's all working, I can hook it back up to the transformer and try again. Okay, transformer hooked back up, so I'll plug it in, do a voltage check across here. Got 15 volt minus there, plus 15 volt there, 38 volt there, plus, and minus 38 volt there. Brilliant. So next comes unplugging it and actually hooking it up to the power amplifier and a oscilloscope here, and actually do the power measurement test now at these voltages. So that's the next thing I'm going to do. Okay, I've got everything hooked up to the power amp now. I've got it across the dummy load, across the oscilloscope input on a ×10 probe. I've double checked that there is nothing shorting and that all the wires are wired correctly to the relative points they should be. So now to plug the transformer in. Nothing immediately apparent. And if I do a blurt test on the power amp, I can actually see there is a blip on the scope. Good old blurt test. As you can see, the yellow trace is moving. So that's on ×10 obviously, so you're not going to see much. Okay, I'm just going to double check my voltage rails now and make sure that they're roughly where they should be now that the thing's loaded down. Plus, still got plus 38, which is pretty good, and minus 38, so there's still 38 volt there. That's good. Now, okay, I got the function generator sitting on the desk over here, just in the corner, just sort of like hanging out. I've got a amp meter in line with the positive rail just to see what the current draw is. The DDS is set to 1 kilohertz 1 volt, and now if I just untangle myself here, make sure nothing's going to come in contact with each other. This is like really a pain in the ass now. Okay, so now I'll plug it in. And I can see I've got about 400 milliamp draw, so about 0.4 of an amp there, and that's running at 1 volt. And we've got a nice stable output sine wave. We're currently at 1 volt per division, so we're looking at, it would help if I actually added the other stuff that I need to see, which is the peak to peak. and the frequency. That's all I'm interested in. So we're at 21.6 volt. Yeah, alright. Now they say that this input sensitivity is 1.36 volt RMS. Now there is a big difference between RMS and peak to peak. So say we had a sine wave of say 2 volt peak to peak. That'd be 1 volt peak. We basically multiply that by 0.707 and that gives us our RMS value, which is in this case 0.707. So again, if the peak to peak voltage was 4 volt, that'd be 2 volt times 0.707. That gives us 1.414 volt RMS. So to work out what that is, so it's 1.36 volt RMS. If we now divide that by 0.707, it's actually more closer to 1.92 volt peak. Multiplied that by 2, that's 3.8 volt roughly peak to peak. So that means the DDS needs to be sitting close to 3 volt peak to peak at its input before we get full output of that power amplifier. And so if I change the amplitude now to what was it, 3 volt? 3 volt. We're now at 3 volt and we're clipping substantially, so I will turn the amplitude down until it stops clipping, which is about there. So we're looking at 2.5 volt peak to peak for full output at the moment, and we're getting 53.3 volt peak to peak. We're drawing about 1 amp thereabouts at just before clipping, so those windings on that transformer are rated at 3.6 amps, so that's totally well within its rating. So I might drop that back off to 1 volt because there's no point running it at full power, it's just going to heat up for no reason. Put it back to 1 volt. The heatsink's getting mildly warm. That heatsink will be going. I've got the proper one that actually that kit was designed around in the first place from Altronics coming on the way. Okay, so we had 53.3 volt peak to peak. Divide that by 2. Gives us 26.6. Square that, 26.65. Gives us that. Divide that by our resistive load of 8 ohms. That is approximately 88 watt, almost 89 watt. So it's pretty close to 90 watts. It's supposed to run on plus minus 57 volts, but I'm running it on plus minus, we'll say 36. And it's producing 88 watt, as opposed to the 115 that it's supposed to produce into 8 ohms. So we're pretty close. Okay, I got the preamp hooked up to the power supply. I've also got it hooked up via 1 lead to the input of the power amplifier. Up there, I only need 1 because it's already got a ground return anyway. That's going into that crap 16 ohm speaker on the floor. Just for shits and giggles, I've still got the oscilloscope hooked up across the output of the amplifier. Why not? So I'm just going to prop this under the light, plug the lead into the input, grab the other end of the cable, and I'm going to plug in the amplifier now. Yep, it works. Albeit there's a buzz there because it's, well, let's not terminate anyway. Okay, got the bass plugged into it now. Let's see what happens. Okay, so let's give it a little bit of bass. of practice on that song. It's kind of hard doing it because I haven't actually played the damn thing for a long time. So yeah, that's working. It actually sounds better now than it did on that Class A amplifier because I'm actually using a better power amp and it's not distorting early. So yeah, I've just proven now to myself and, well, anyone that's watching, that the preamplifier is performing well, the power amplifier is performing well, the power supply is working with it, and the transformer, choice of transformer, is also working with it. So next thing to do would get the speaker protector working when I get it, and I've got a rack mount case on the way as well, so I will be assembling that into a rack case, doing some labelling and stuff, and finalising the project and changing the heatsink. But other than that, it's working, and it's working great, and I'm happy. So yeah, I'm going to end this video here. Thank you for watching, and I'll see you again in the next one. Ciao for now.